the constant of integration. Constant of integration. It doesn't matter whether you put it inside the parentheses here or outside the parentheses. You could just write it down, constant of integration. This kid in my class said, but if you put the C on the inside of the parentheses, wouldn't it be half a C? He's asking questions like that all semester. I felt like taking my book and throwing it at him. Asking questions like that. I was like, oh. It's a constant. Doesn't matter. I mean, all right, okay. So now we multiply this stuff together. Two negative signs cancel out here. And one factor of the capacitance cancels out. And so what you get is you get E divided by R. Or the E minus T RC. There's your current in the circuit. Your current. And over here's your charge. So if we look at current as a function of time, the current just exponentially decays from its maximum value. Oops, exponentially decays, so it approaches 0, it never quite gets there. That's not a very good explanation, but that's supposed to be exponential decay. And that's what it does. All right, so let's take a look at the limiting cases here. Let's take a look at the limiting cases.
So does it decay to I, or does it decay to, it should decay to I, right?
No, this is I. That's a function of time. Okay.
But assuming that we're going to have a constant current throughout the circuit, it's going to...
Oh, it's not going to be constant. It's going to change as a function of time. We don't have a constant current anymore.
But once all the charge using the circuit.
Oh, once all the charges are, well, let's see what happens. Okay, let's see what happens, okay? All right, so let's take a look at the two limiting cases here, okay? And so let's make a little chart here. First of all, we're going to look at T equals 0, okay? And I'm going to look at the charge in the circuit. And I'm going to look at the current in the circuit. Okay? So at T equals 0, let me pull this up. Okay, so T equals 0, and I want to look at this. All right, so here we go. I put 0 in for time here, 0 in for T, all right? Negative 0 is what? 0. Okay, 0 over R times C is what?
0.
0. Okay, 0 divided by R times C. E to the 0 is what?
1.
1. 1 minus 1 is what? 0. 0 times EC is what?
0.
0. So the charge at time 0 is 0. That's good because that's what we said we started with. We're starting with this uncharged capacitor. There it is. Okay. All right, let's take a look at the current at T equals 0. Here's the current equation. All right, so plug in 0 for T. Negative 0 is, no, negative 0. 0. 0 divided by RC is
0.
0. E to the 0 is
1.
1. 1 times E over R is
ER over R.
E over R. There we go. Now notice that this current that you start out with at T equals 0 is just the voltage divided by the resistance. That would be the current in the circuit if the capacitor weren't even there. If the capacitor weren't even there. Let's take a look at the other limiting case, which is what we call a long time. Long time. Long time in mathematics is, what's a long time in mathematics?
Infinity.
Infinity. So we're going to look at T equals infinity here. All right? All right, let's take a look at the charge, right? Okay. Put infinity in here. Infinity divided by RC is what?
Infinity.
Infinity. Okay? E to the negative infinity
Approaches 0.
is 0. Okay? Because it's 1 over e to the infinity, 1 over infinity is 0. 1 minus 0 is 1. 1 times EC is EC. Okay? take your current, take a look at the current. Put t equals infinity in for here, okay? Infinity over RC is infinity. E to the minus infinity is
0.
0. 0 times e over r is
0.
0. Current goes to 0. Current goes to 0. Okay? So these are the limiting cases of your capacitor. These are the limiting cases of your capacitor. Now here's the principles to why. Here's the principles of why. Okay? An uncharged capacitor acts like a reservoir because you could store charge on the capacitor itself. Current cannot flow across the capacitor. It has to flow on one side and off the other. So if the capacitor is uncharged, when the capacitor is uncharged, there's plenty of room for the charges to flow. Plenty of room to dump charges. So an uncharged capacitor acts just like a wire in terms of the current flowing through it. It doesn't interfere with the current. If your capacitor is uncharged, it will not interfere with the current, because there's plenty of places to dump charges on either side of the capacitor. But as that capacitor starts building up charges, these charges are going to repel any other charges that I try to put on there, i.e., it's going to start hindering the current that I put on it. Once the capacitor is completely filled, well, there's no more room for charges, no current can flow. That's it. It's full. I can't put any more charges there. There's nowhere else for the current to go. The current has to stop. That's what happens with the capacitor. So a fully charged capacitor, once it's already charged, it acts like a gap. You can't put any current through it because there's no place for the charges to go. So as long as the capacitor is charging up, as long as it's still got places to put the charge left, current can flow. But once it's charged, that's it. And that's why what happens here is that the charge builds up, the current goes down. The other way to look at these functions here, these two functions, are the voltage across your capacitor and the voltage across your resistor. So let's look at those two things, the voltage across your capacitor and the voltage across the resistor as functions of time. Okay, so voltage across the capacitor. Voltage across the capacitor is Q over C. So if I take this top equation and divide it by C, what happens? Well, the C cancels that C, and then you just have the E. So this top equation simply is E times 1 minus e to the minus t over RC. Resistor, I take the current multiplied by what? Voltage across the resistor is equal to the current multiplied by the R, the resistance. Where do we get that? Oh, okay. Where do we get that? So you multiply this by the resistance, what do you get? You get E. There we go. E to the minus t over RC. So if you look at what happens in terms of the voltages as a function of time, the voltage across your capacitor, scooted up. Yeah. Lots of graphs here, Bob. So it builds up. And the voltage across your resistor. Okay, so here's my VR. And up here's my DC. Yeah, green is capacitor. Right? Green is capacitor. Now, of course, if we look at this, let's take the sum of these two. Add them up. Here I have e minus e to the minus t over rc plus e times e to the minus t over rc. So what happens is this negative e to t, I'll just write that. E minus e to the minus t over rc plus e minus t over rc. And what do you get? E. Does that make sense? Yeah. This is a DC circuit. The sum of the two voltages has to be equal to the voltage of the battery. So at first, all of the voltage is across the resistor. You've got current flowing through, and there's no voltage drop across the capacitor. Okay? After a long time, all the voltage is across the capacitor, your capacitor is fully charged, no more current in the circuit, 0 voltage across your resistor. All right, so we've taken a look at these limited cases where we have t equals 0 and t equals a long time. So now we want to ask a long time compared to what? What do you mean long time compared to what? Long time compared to a day? Is a day a long time? Is 3 minutes a long time? Is 2 seconds a long time? How long is a long time? How long is a long time? So we want to look at this. Let's take a look at this equation here, and I'll rewrite it on a new page. Let's take a look at our equation here. Okay, so Q is a function of time. EC times 1 minus e to the minus t over RC. All right, now, all right, what I want to know is what is the 2 to the power of 3 meters? Okay, what is that? 2 to the power of 3 meters.
3 meters?
Yeah, 3 meters. 2 to the power of 3 meters.
8 meters?
What about 5 to the power of 2 kilograms?
It don't quite make sense.
It doesn't make any sense.
No.
If you have an exponent, you can't have units in the exponent. How do you take something to the meter power? That doesn't make any sense. It makes no sense.
You just take
Okay.
like the log of it.
So what that means is that this exponent here has what kind of units? None. It can't have any units. So the exponent there, that can't have any units. No units there. All right? So that means that T over RC has no units. T has units of what?
Seconds.
Therefore, R times C has to have units of what?
Seconds.
Seconds. And so what we talk about when we talk about this quantity, R times C, that is a time constant, tau. R times C. Okay? It's a time constant. It basically relates as to how fast that capacitor is going to be charging up. And the units of that are seconds. So if I take an ohm multiplied by farad, I actually get a second out of it. Now, depending on kind of what circuit you're dealing with, you know, like if I have a capacitor of 200 microfarads and a resistor of, 30 ohms, if you multiply this out, the time constant is like 6 milliseconds. Okay? So there, 1 second is like, my goodness, you get like hundreds of time constants for 1 second. 1 second is a long time. You throw the switch closed, that thing's pretty much charged up. Okay? It basically, you throw the switch closed, it would probably be charged up before you could even react to flip it back open again and stop it. So this case there. Of course, then again, I could take that same, let's say the capacitor is, I don't know, maybe it's only 30 microfarads, but my resistor is 5 mega ohms. Okay? 5 mega ohm resistor. It's easy to make 5 mega ohm resistors. Man, just stick some kind of nice insulating material. There you go. It's not hard. 5 mega ohm resistor here. Woo. Okay, so let's see. Well, in this case, the time constant would be 150 seconds. 150 seconds. We want to wait for several of those time constants to pass by before we could say that the capacitor would be completely charged. Completely charged. We could actually do a mathematical exercise. Let's say that we want our capacitor to be 99% charged. Okay, we want the capacitor to be 99% charged, and I'm going to do a mathematical exercise to see how many time constants it takes to do that. Okay. First, what I'm going to do is I'm going to talk about Q. Let's see, Q over Q max. Okay, and the time is I'm going to put in this column. Of course, when I say the time is 0, right? The time is 0. 0 time constant, then of course Q over Q max will be 0. After one time constant, tau, okay? After one time constant, tau. So I need some calculator people to do this because it's been a while. I think I know what the answer is, but I'm not sure. I think I've remembered it, but I'm not sure, so please bear with me, okay? So somebody take e to the -1, and then take 1 minus that, and calculate what it is. Because after one time constant, that's what you're going to get. So e to the -1, 1 time constant. What'd you get? 0.632. Okay, that's so basically you've got about 63%. So the capacitor's 63% charged after one time constant. Okay. All right. What about 2 time constants? Let's look at 2 time constants here. So now take e to the -2, take 1 minus that number, and tell me 86. All right. 86. Okay. So even in that second case, you wait 300 seconds, it's 86% charged. Okay. After 150 seconds, it would be 63% charged. All right. So now we're going to go the other way. This one mathematics is a little bit hard. I want 99% charge. I want to know how many time constants it takes to get there. How many time constants does it take to get there? Okay. So you guys who love this mathematics, right? You love math, you love working with. So here's how to do it, right? So we put Q as a function of time. We want that to be 99% of the maximum charge. Maximum charge, by the way, is what number here? Or what in this equation? EC. That's your maximum charge. Your EC is maximum charge. So this one is 0.99 EC is equal to EC times 1 minus e to the minus t over RC. There we go. All right, so divide through by EC. So this is 0.99 equals 1 minus e to the minus t over RC. Subtract 1 from both sides, negative 0.01. Multiply through by -1 to get rid of that negative sign. Now what do? LN. And I'll go ahead and put a tau here, because that's our time constant, our time, see? So what's the natural log of 0.01? Negative 4.61, okay. Notice the negative signs are going to cancel again. I multiply through by tau, and I get that the time for 99% charge is equal to 4.61 time constants, tau. So if I wait 4.61 time constants, my thing will be 99% charge. So far, so good? Kind of understand how this thing works?
Is this for general or is this for the example of the 115?
Oh, no. This tau equation here, this is general. Because I didn't put in 150 for tau. Now, if I want to know exactly how many seconds for that particular circuit, I'd put 150 seconds for tau, multiplied by 4.61, and then I can find exact how much time it would take actually to charge at 99%. Okay? Yeah, tau is just, this is the Greek letter tau. Okay. Usually when we talk about the little t in any equation, we're usually talking about a variable time. You know, the time is, so many seconds it's varying. It's a clock that's moving. When we either use capital T, which we'll use for period, those functions, period or something, or a tau like this, it's a constant of the circuit, or it's a constant of the system. That doesn't change. See what I mean? Yeah.
For like the previous example, you don't need to go back there.
Okay.
But like you said, microfarads and mega ohms, those micro and mega wouldn't affect.
Oh, they.
seconds or what?
Well, they do. You see this micro? That's 10 to the negative 6. There's a specific reason why I chose micro and mega here. Okay? Because this micro is 10 to the negative 6. What's the mega? 10 to the 6th. The product of these two things is 1.
So the one above it would be microsecond?
Yes, the one above it would be 6,000 microseconds, which is 6 milliseconds.
Okay.
So, yeah, let me go ahead and put this here too. So this tau here is equal to 6 milliseconds. Okay? So in other words, for this thing to be 99% charged up top, I have to wait about 25 seconds. Or actually, maybe a little bit more, because it's 4.6. So it's like 24.6, about 3. I'll add 4 to that just to be sure. So I got 28 seconds. So I have to wait about 28 seconds, and that thing's milliseconds, and that thing's 99% charged. Okay. Here I have to wait quite a while. Okay. 4.61. 6,000 per second, about 10 minutes. All right, now, this isn't the only thing you can do. This is not the only thing you can do with capacitors. The other thing is you can take a capacitor that's already charged. You can take a capacitor that is already charged. So I can take a capacitor that is fully charged. So here I'm going to start with, which side of this do you want me to make positive? The left? Okay. So I got plus Q, minus Q here. Now I'm going to take a switch, and I'm going to hook it up to a resistor. See, because remember what we can do with the capacitor is we can then use that energy stored in the capacitor to run other circuits. We can actually use the capacitor to drive a current. We can use this capacitor to drive a current with its charge. So let's see what happens when we do. Now in this case it's a little different because I would have to draw my loop equation like so. So I can go from the negative side of the capacitor to the positive side. Once I close this switch, the positive side charges are going to flow around this way back to the negative side. So the current is going to be flowing through this. And so what I would get for my differential equation is that as functions of time now, Q over C minus R di dt, whoops, dq dt. Where did I get the dq dt from? dq dt is current equals 0. So what I get here is I get that the Q as a function of time is the charge I start with multiplied by e to the minus t over RC. And my current, and I'm going to go ahead and do this, e to the minus t over RC, where the current that I start with in this circuit is the voltage across that capacitor divided by the resistance. So it's equal to my Q naught divided by RC. I should have RC instead of that. That's what my Q. So in this case, this is what we call a discharging capacitor circuit. In this case, the voltage across the capacitor and the resistor are the same. And the capacitor discharges through the resistor. Notice the time constant still pops up. The time constant still pops up. And so what happens is that the current and the charge on the capacitor, that is Q naught, charge on the capacitor goes down exponentially. If I have an I naught, the charge on the current also will decrease exponentially. Basically, and the voltages all decrease exponentially as the charge runs off the capacitor. So now when the capacitor is driving the circuit, when you start out with the capacitor, you start it with your maximum current because the capacitor is now driving it. But once all the charge is gone, there's no more current. In fact, there's no more anything after all the charge is gone here. So in this case, at t equals 0, when you're discharging something, when you're discharging, so this is discharging, because we are now taking the capacitor and we're discharging it. At t equals 0, the Q is equal to its maximum, and the current is equal to its maximum. And when all is said and done, once the capacitor is discharged, well, there's no more charge because it's discharged. Once it's discharged, there's no more charge because it's discharged. Charge. So the charge is 0. And since that charge is what was driving the circuit, because we basically take a capacitor and we're trying to use it like a battery. We're trying to use it like a battery. We're trying to drive the circuit with the capacitor. Yes, t is infinity. That's a little infinity. Okay. The current goes to 0. And once again, how fast this happens depends on what your resistance and capacitance are. Okay. Now here's a thing for you. Let's say that I start off with a discharging capacitor. Okay. Start off with a discharging capacitor. At t equals 0 seconds, the charge on my capacitor is, let me be simple and exaggerate, it's 10 coulombs. Okay? I suppose it gets, let me be more realistic, 10 microcoulombs. Okay? 10 microcoulombs. Okay? Now I've done this in such a way that after 10 seconds, right, the charge on my capacitor is 5 microcoulombs. 5 microcoulombs. All right. After 20 seconds, nobody say anything. Put down what you think the charge should be on a capacitor after 20 seconds. Okay. All right. Let's look at some answers. What'd you get for it? You gave up?
2.5.
You got 2.5. Anybody else get something besides 2.5? Did anybody say 0? That's brave enough to, okay, good, thank you. By the way, that's wrong. But thank you. But thank you. Notice that this is exponential decay. It's just like every other exponential decay. The only thing is instead of describing the time, we describe it as a time constant, which is our time c. But we could come up with a different time, because it's an exponential decay, as in a half-life. So in other words, this isn't a half-life, it's a 37% life, I think. It's a 37% life because of the nature of the natural logarithm and the fact that when you put RC in there, it's 37%, it's not, 50%. Okay? But it works the same way. It's still an exponential decay. So in other words, if half of it's gone after 10 seconds, half of that will be gone after the next 10 seconds. And after the next 10 seconds, half of that would be gone. It's an exponential decay. It acts like every other exponential decay. Okay? No. Because if I did that, I'd have to take off of these poor brave people that admitted that they said 0. And that wouldn't be nice. Nobody would ever admit they got the wrong answer, and then nobody would learn anything. Because the only way to learn anything is to make a mistake and then correct it. So you didn't actually learn anything today. Whereas these two brave people, you learned something, right? Because you said different answers. So then you correct yourself in your head. 2.5.
I never could be born. Also.
Well, yeah, because after 10 seconds, half of it, after another 10 seconds, yeah. If I had I could do it with like 2/3 or whatever of the ratio it is too, in that case. But it's an exponential decay. All exponential decays would work like this. It would do the ratio. You do the ratio thing. Okay. It's a little bit more confusing when you're charging it because it's that difference between the maximum and that decays exponentially. So after like so many seconds, you'd have half of it charged. After the rest of it, half of the rest of it would charge, which means would be 75%. Then 80
something,
87.5%. Then 90. Well, you get it. Okay, you get what it is. So it's that difference that's exponentially decaying, which makes it a little bit more confusing. Okay. So the discharging ones, though, you should be able to recognize. Okay, that's an exponential decay, just coming off like that. All right, now. Okay, now the fun circuits. Let's take a look at this fun circuit. How much fun do you want to have? Oh, let's give you real numbers. Let's say that my E is, we like 5 volts, right? All right, so then we go over here. You want me to keep it simple? All right, 2 ohm resistor here. And let's put a 3 ohm resistor here. And then over here, I'm going to put a 200 microfarad capacitor. And I forgot the switch. Okay, I'm going to put the switch down here. Okay, there's the switch. I close it at t equals 0. Okay, close it at t equals 0. Now with this type of circuit, I will never ask you for the exact time constant. For the exact time constant. It turns out there's a weird thing. There's a weird way because charge could go this way or this way. It actually turns out it looks like well, no, that one, forget it. See what I mean? It's kind of hard to deal with here. But this actually helps. If I put the 2 here and a 3 here, it actually, well, no, that's a little bit more. But actually, it's weird. You'd have to use Kirchhoff's laws to really derive it. There are certain configurations that don't look like they would make a parallel resistor with a capacitor there. If you do have just a simple resistor circuit that's parallel or something, or capacitors in series and parallel, but they're all in series with each other, then you can go back and say that this is the equivalent as the R and the C. But here we have a resistor in parallel with a capacitor. Yuck. Don't like that. Okay? Don't like that. Not in terms of solving my differential equation. Those of you who go on in this, you'll love it. You use Kirchhoff's laws, you get your differential equations, you solve. something to look forward to in the future. But what I do want you to be able to do are limiting cases of this, using the principles that we talked about in terms of your capacitor. Okay, in terms of your capacitor. So the first question of what I'd like to know is I'd like to know what the current in the circuit at t equals 0. So question A, I want current immediately after the switch is closed. Okay? Should I give you B and C here too? I'll just do one at a time. Okay? But you would be asked 3 questions about a circuit like this. Okay? A circuit like this, you'd be asked 3 questions. All right. First of all, you want the current immediately after the switch is closed. And there's plenty of these on the homework too. You get to have lots of fun. All right. Immediately after the switch is closed, and the other thing you'd be told is the capacitor is initially uncharged. Capacitor is initially uncharged. Immediately after the switch is closed, okay, immediately after, the capacitor is uncharged. Uncharged capacitors act like what?
Just wire.
Wires, because they've got plenty of room to dump current. I can dump current in it. So the current, here it comes out of this battery, flows through the 2 ohm resistor, and this acts like a 0 ohm resistor. So all of the current is going to go over here. None of it's going to go through there. So immediately after, this is what it sees. You'll have to think about this when you do it, but immediately after it's closed, here's what it sees. It sees this 3 ohm resistor, and it sees a wire over here, because it can dump the current. Okay? If I put a 3 ohm resistor in parallel with a 0 ohm resistor, what's that mean? It's 0 ohms. Basically, all of the current is going to flow on the capacitor branch. Immediately after the circuit is closed, all current flows on the capacitor branch. All of it. Because it truly acts like a 0 ohm resistor. Because there's no charges to even oppose any charge I'm going to put on there. The charges say, whee! Okay? So immediately after, that acts like a wire. All of your current flows through here. That's all the current. No current flows through that 3 ohm resistor. None. Immediately after it's closed. So how much resistance is to that current? 2 ohms. That's all the resistance. Because none of it throws through the 3 ohm resistor. So just 2 ohms, that's it. So therefore, right after the switch is closed, what's the current in the circuit? 5 over 2. 2.5 amps. There you go. Ta-da. Next, ready for the next one? Next, I will ask you. Current a long time after the switch is closed. Current a long time after the switch is closed. Okay? All right, so after the switch is, a long time after the switch is closed, this capacitor will be what?
Fully charged.
Charged. Once this capacitor is charged, how much current can flow through it?
0.
0 current can flow through this. Can current still flow in this circuit?
Yes.
Yes.
Over the
But
3
it all
ohms.
has to go through the 3 ohm resistor. So current still flows in this circuit. It just all goes through the 3 ohm resistor. Okay? So this time, all the current flows through the 3 ohm resistor. So therefore, how much resistance do we have now? Think about it.
5.
A long time afterward, if I go through, I have to go through the 3. There's no other place to go. So it's 5. I have to. So that's 5. So therefore, the current in this circuit is 5 volts divided by 5 ohms, which is
1.
1 amp. 1 amp. Hooray! Hooray. 1 amp array. All right. Now ready for the next question. I want to know what the charge stored on the capacitor a long time after the switch is touched. Okay. Charge on capacitor a long time after the switch is touched. Well, how do we find that? Well, let's see. Well, I could find it if that 3 ohm resistor weren't there, right? Because then I'd know that that voltage across there would be the voltage across the battery. I'd know that the voltage across here would be the voltage across the battery. But the 3 ohm resistor is there. So the goal here is instead of worrying about finding the charge, think about it. If I know the voltage across that capacitor, then I know what the charge on it is, if I can find the voltage across it. The voltage across this capacitor will be the same as what? Okay, you got 3 choices here. Battery, 2 ohm resistor, or 3 ohm resistor. Or switch, I guess, 4 choices. So, how many say the switch? No, because you can even use psychology. I threw that in at the last second. Your main choices are the voltage or the 3 ohm resistor. Here's the way you do it. You have to look for something directly in parallel with the capacitor. Direct parallel will tell you. And that's the 3 ohm resistor. It's in direct parallel. You know what I say by direct parallel? If I want to go from A to B, notice I can either go through this or through this. These 2 voltages must stay the same. By the way, it would be the sum of these 2 voltages if you wanted to do that. Okay, if you wanted to get fancy, yes, it would be the sum of these 2 voltages. But it's simpler to say, oh, it's just a voltage across this 3 ohm resistor. Everybody see that? Because it is directly in parallel. I can go through this or I can go through this. Those 2 have to have the same voltage. So the final voltage across the capacitor, so final voltage across the capacitor is equal to the voltage across the 3 ohm resistor, which is equal to the current through the 3 ohm resistor. How much current is across the 3 ohm resistor? 1. We just solved for it. We just solved for it. You know, I got an idea. You know, he's making a video, and I understand that sometimes, you know, I do talk fast. I've been working through this for years, and I love it, and it's all exciting and everything. But you might want to slow down the video so that your brain can keep up with somebody who's done this for 30 years.
You sound like Dory doing the whale impression.
Okay, so 1 amp multiplied by 3 ohms is equal to 3 volts. So now I know that there's 3 volts across this capacitor. Okay, and so let's find out what the charge on the capacitor is. The final charge on the capacitor is 200 microfarads. Sorry, it's the voltage across the capacitor multiplied by the capacitance itself. And notice I'm beginning to start labeling these voltages when I write them down. You know, because it's the voltage across that particular capacitor multiplied by the capacitance. Okay? Because we want to keep track of which element we're talking about. Like the voltage across the 3 ohm resistor is the current through the 3 ohm resistor multiplied by 3 ohms. Okay? So in this case, it's 600 microcoulombs. All right, here we go. Ready? One more thing. Now I'm going to draw the circuit again. I'm just redrawing the circuit so I can have it at the top of this page here so I don't have to keep going back to the top of the other page. All right, now, my circuit switch has been closed for a long time. Okay, a long time. By the way, I can tell you that it wouldn't take very long because the order of whatever time constant I come out with this is going to be something microseconds. It's not, it can't be any more than, yeah, so. All right. Then I restart the timer at t equals 0 and open the switch. So I open the switch and restart the timer. And restart the timer. And question D is then, write the charge on the capacitor as a function of time. Write the charge on the capacitor as a function of time. Okay, so now I'm going to open the switch. So now I open a switch at t equals 0. Once I do that, once I open the switch, what happens to this part of the circuit? It's broken. Therefore, how does this part of the circuit affect the other part of the circuit?
Doesn't.
It doesn't. It's gone. It's gone. Gone. Once I open that switch, that's gone. So now what's going to happen? I waited a long time, so I have my positive charge here, my negative charge here. What's going to happen after I open the switch? It's going to start discharging.
Through the 3 ohm.
So it's going to start discharging through this 3 ohm resistor. That's what's going to happen. It's going to start discharging through the 3 ohm resistor. So when it does, it looks like this. So let's write down the basic equation for our discharging capacitor. So Q is a function of time for discharging is equal to Q naught multiplied by e to the minus t over RC. Now, as confusing as it said to write down the charge as a function of time, right? As confusing as I said, it's not that hard. Because the only things I have to worry about in this equation here, I've already got the basic form of the equation right here, are Q naught and RC. That's it. Because everything else is given for you. When I tell you to write it as a function of time, you just use the basic form and then plug in for specific numbers. So how much charge do we start with? 600 microcoulombs, what we had from before. So my Q as a function of time is going to be 600 microcoulombs. I'll even put units in this equation too. I have to be careful when I put my units because from now on, I want to put them in parentheses like this. Do you know why? I don't want you to get confused with this C as the variable capacitance. That's the unit of coulombs. Okay? Now I want to plug in for R times C. So the C, I know, it's 200 microfarads. So what R do I use in this equation? 3 ohms. So that gives you 600 microseconds for the tau. So the tau in this circuit is equal to 200 microfarads multiplied then by the 3 ohm resistor, or 600 microseconds. And so then I would simply write e to the minus t divided by 600 microseconds. Coincidence, by the way, that these two are both 600. And it's because it chose such simple numbers, that this 5 volt resistor, so that, yeah. Go ahead.
Can you explain why we ignored the left side again?
Because it is broken. Once you break it off, no current can flow through this thing. Because there's nowhere for it to go. So the battery, if I connect one side of the battery to something, it doesn't do anything. Because I need to connect up the other side. So that battery can't push current out because there's nothing that can go into it. So you can't have, so in other words, the battery's not going to push current out one side without something to pull it back in the other side. It's not going to work. Have you gotten to your RC circuit lab in RC in lab yet? That's this week. Well, at least I get to it right before you do it in the lab. Now, I want you to get into your groups and exchange information. I do want to put up a group problem for this topics, and so. No. I want you guys to work in groups. I really do. I don't want you to back off working in your groups just because this material is easier. Okay? I know that this material isn't quite as intimidating as the stuff that we just got through. Okay? But I want you to keep that, you know what I mean? I want you to still keep that work level up. Okay? All right, so get in your groups, talk about it. And in the last few minutes, if you weren't here on Monday, if you were not here on Monday, I did get the tests back, and I do have them with me. So you guys just come see me. And so anybody else who did back on Monday?
When you do it within the 10 days after, you have to credit.
If you do it the next day, it's worth 90% of what it was. If you do it the day after that, it's worth 80% of what it was. Yeah. So just do it. Yeah. Good morning. Okay. You know where we are. All right, so right here, we're now going to start looking at a circuit with both an EMF, a resistor, and a capacitor. So far, what we've done is we've assumed that all the capacitors, as soon as you switch the battery, are all charged. You know, we say it's instantly charged, or we wait until it's charged, or we've only been examining circuits with the capacitor charged. Now we're going to take a look at actually that process of charging a capacitor, and the process of taking that capacitor and then discharging it. So we're going to look at the transition here. All right. So we have is what we want to do is we want to form a equation to deal with this. So we say that the capacitor is initially uncharged. So we're told to know that, and we throw the switch. The switch is closed at t = 0. And what we want to do is we want to find out, what is the charge and the current in this circuit as functions of time. So we want to find out charge as a function of time and current as a function of time. Okay? So we start with an equation. So we close it, and we're going to literally use a Kirchhoff loop equation like this. In other words, where we set the voltages around this loop, and we set that sum equal to 0. We set that sum equal to 0. So the first thing we get to is we get to this battery here. Okay, it's an EMF. I'm going from the negative side to the positive side. So I have the current in the circuit will flow through here. And the charge on the capacitor, there will be a positive charge here and a negative charge here. And this will help us deal with the other two circuit elements. When we talk about the voltage across the resistor, our loop is going to go in the direction with the current. And so we're going to subtract off the I, and I'll use a little letter I just because I want to focus on that as a function of time, multiplied by the resistance R. Okay, we're subtracting that off. We then also are going from the positive side of the capacitor to the negative side of it, so we're going to subtract that off as well. So we minus Q over C, and that equals 0. And there we are. That's the equation that comes out of Kirchhoff's loop law for this particular circuit. Now, a couple problems that you see with this is that it looks like there are two variables, but there's only one equation to deal with. And we don't have any junctions here. It's just one loop. It's just one current. That's it. Okay? But the charge on the capacitor is related to the current, because this current is flowing onto the circuit is what is charging the capacitor. So the amount of charge that flows onto the capacitor is the amount of charges flowing with the current. And so we use a definition of that current, which is dq dt. And so what you get is an equation that looks like this. Where here Q is a function of time. Where here Q is a function of time. Okay, now, those of you who've gotten that far in math, what is that? That is a first order differential equation. Okay, you haven't gotten that far yet. Okay? You have not gotten that far, most of you haven't gone that far. So it's not required, you know this, but eventually, especially when you take your upper division classes in electrical engineering, you'll be expected to be able to solve things like this because you will have gotten there by that time. What we do here is we tell you what the solution is, and you can see how that solution works. Okay? The solution to this equation is that Q is a function of time. Okay? Is equal to C multiplied by 1 minus e to the minus t divided by r times c. Okay. That's the solution to the equation. By the way, you also need to use the limit in this equation here because the first order differential. You need to use your limiting case that Q at time 0 is 0. It begins uncharged. So those of you who have gotten that far, that's how you get this equation. Because Q times 0 is 0 because it starts out uncharged. Okay. All right, so let's see. Let's see what what this looks like. If I were to graph this, like this. Okay, the maximum of this is the E times the C. And what starts out as a Q to 0, and it exponentially approaches that line. as time goes on. So when you start out, it charges very fast. Very fast, and then it slows down, and at long time, it's going to be equal to this E multiplied by C. Now, if you notice, this is the voltage times the capacitance. This EC that it approaches is as if this resistor weren't even there. So in other words, eventually this whole thing charges up, and it's fully charged capacitor. Okay? Now, we can actually find the current in the circuit. I could give you the equation, but let's get some practice in. It's this, QDT. So let's take this function, and let me multiply this stuff out. So I get EC minus EC, e to the minus t over RC. This part you should know. Okay? This part you should be able to do. All right, let's do this. Hopefully you can, right? Just remember that these two things are constants. This is the, yes?
Then E.
Is the voltage. The curly QE is the voltage of the battery. Okay? Oh, this little e. This little e is the exponential, the inverse natural logarithm of 1.
2.7.
7 blah, 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 whatever that number is that turns out to be. Okay? That e, the exponential function. Okay? That is not the electronic charge. That doesn't make any sense. Okay? All right, so e times c. When I take a derivative of these things, this is a constant, so what happens to it? It's 0. So the derivative of this is 0. Okay? So I'm just going to take the derivative of this term, so I'm going to pull this constant out in front of this stuff, and I want to take d dt of this. Okay? This is a what kind of function? Exponential. So therefore, it is the exponential itself multiplied by the derivative of the exponent. The derivative of the exponent, this is a single power of time here. So just the coefficient comes down, so it's minus 1 over r times c.
What was the first EC 0?
Oh, because the derivative of a constant is 0. It's okay. I had better questions in my calculus class. I would have wrote it something to somebody. My calculus teacher was doing an integral. She had this integral here. And what happened is it turned out to be 1/2 times a certain integral. Okay, 1/2 times this integral. And then she did it, and she got 1/2 multiplied by stuff. And then she said, well,